Hello and welcome to this electropotentials exam question walkthrough. It's going to cover quite a lot of different skills, all of which are important to make sure you're confident at, to enable you in any A-level paper which covers electropotentials to be confident at getting maximum marks. So each section of the question deals with one of those skills in turn. So having a look at the whole question, let's think about processing it as a whole first before we start looking at the individual parts. So taking a quick look through it, you can see the first part is a definition, the second part is a calculation, then you've got an application question which is more demanding, then a recall part which is requiring you to recall something quite subtle and nuanced from the sort of specification. Then there's a simple recall of how to draw a standard hydrogen electrode. Then an application question, another application question. So the last parts are quite demanding. It's balancing using oxidation number. But what you'll see quite a lot of is what comes from learning your flashcards, what comes from past paper question practice. So a bit of both types of revision skills are needed to be successful in this particular question. So it challenges candidates quite well. Let's have a look at the definition first of all. So what is a standard electropotential? It's basically the difference in volts between the electromotive force of a half cell and that of a standard hydrogen electrode. So the electromotive force is basically the force pushing the electrons around a circuit. It's measured in volts, and each individual half cell has a slightly different EMF, or as we say, standard electropotential. So it's just the difference between them. Now, if we just say difference, that means we assume it's the same difference all the time. Conditions can change that makes that difference not the same every time. That's why it's the potential difference. So for this to be a standard electropotential, it must be measured at 298 Kelvin, 100 kilopascals of hydrogen gas pressure in the standard hydrogen electrode, and the ion concentrations on both sides, on the positive and the negative half cell, have to start at 1.0 mole per decimeter cubed. So the mark scheme reflects all of this, and it gives you a little bit of flexibility as well in how you actually express voltage. So let's now go to the next part of the question, working out the cell potential. So it directs you to redox systems 1 and 2 from the table, and what you need to be able to bring to this question is having memorized how to calculate E cell. So once you've done that from your flashcards, you can then plug these numbers in quite easily and then get plus 2.71 on your calculator. So that's what it's got on the mark scheme, but it says this time, in this particular mark scheme, that you can ignore any sign. Be careful, because that's not necessarily what you'll be able to get away with every time. So put the correct application of the E cell calculation, and then you'll get the correct sign. Technically, minus 2.71 would be wrong here. So this is where it gets a bit more challenging, predicting reaction feasibility. So a couple of things you've got to bear in mind here. So you can see I've put redox systems 3, 4 and 5 at the top for us to refer to. And any pairing of two half cells, the more negative one will proceed as an oxidation. So that means that the right-hand side species will be the reactant in this case. Conversely, if you have a reduction, the left-hand side species will be the reactant. So you need to bear in mind that they're asking for 3 reactions that might be feasible, but there's more than 3 possible combinations, isn't there? So don't just go in and randomly start putting things together and hope that the right answer is in there somewhere, because like I'll explain with the mark scheme a bit later, they penalise you for that approach. So let's take each one in turn. With the aluminium, it's the most negative electropotential, so it's definitely going to be reversed. So Al3+ cannot be a reactant. With the iron 3+ to iron 2+, it's the most positive electropotential, so Fe3+ cannot be a reactant. This cannot be reversed when paired with either of those other two, so Fe3+ must be the reactant. So that eliminates not only Fe2+, but also Al3+ as potential reactants. Where you've got to do the thinking is, which pairings will iodine be reversed with? Because the half cell, the iodine iodide half cell, electropotential value is more negative than that of Fe3 plus Fe2 plus, but less negative than that of Al3 plus Al. So the conclusion here must be iodine will be reduced by aluminium, but iodide will be oxidized by Fe3 plus. So let's pull those deductions together. So starting out with Fe3 plus and aluminium, Fe3 plus will be reduced. It'll proceed from left to right because it's the more positive of the two. Now you'll also see that there's only one electron being gained here, so the reduction, the Fe3 plus equation, has to be multiplied by 3. So that's why the balancing numbers in front of the iron species say 3. So that's still going on with this pairing between 2I minus and Fe3 plus. You'll notice that I've had to double up the number of Fe3 pluses and Fe2 pluses because again I have to make the electrons balance. The Fe3 plus only gains 1 electron, but the iodide, because there's 2 of them to make an I2 diatomic molecule, must release 2E, 2 electrons in total. So finally we're looking at aluminium and iodine, and those two react to make 6 iodides and 2 Al3 pluses. I've got to do a bit of multiplying up here as well. So the iodine iodide multiplies by 3 and the aluminium 3 plus aluminium is multiplied by 2. So that gives us these 3 possibilities that you get marks for. Now like I said earlier, don't just do random combinations and hope the right answer is in there, because if you can see the guidance, it says mark incorrect equations first. They want you to think about this. They don't want you to just jump in and just throw stuff at them. So think carefully about what things you pair together in the way that we've gone through in the last couple of minutes. The next question asks about considerations other than electropotential values. So it says give 2 reasons why it's uncertain whether reactions predicted from electropotential values may actually take place. The first consideration is the temperature. It might not provide enough energy to overcome the activation energy of the half cells. That could also affect the rate of reaction. And then the concentration of the ions, particularly as the cell starts to run, might not be 1.0 mole per decimeter cubed anymore, as the position of equilibrium starts to shift away from the predicted direction of the half cell. So those things are captured in those 2 marking points. Don't write standard conditions are different. Now let's take why that is wrong in a second. Standard conditions relates to specifically 208K, 1 mole per decimeter cubed, and if you're using a standard hydrogen electrode, 100 kilopascals of gas pressure. If you say standard conditions are different, then, well, they're not standard anymore, are they? So it's a contradiction without you realizing, so don't fall into that trap. Now the next bit, we said, gets a bit easier. It's completing an electrochemical cell diagram. So I'm going to apologize in advance for the quality of my sketch. It's a bit dreadful, but I've had to draw on my screen of my laptop to try and do this. This is my 4th attempt to do it, so hopefully it's reasonably clear what goes where. So don't forget it has to be labelled up in the correct way. And just to be on the safe side, I also put 1.0 mole per decimeter cubed on the right hand side next to where they put Cu2+. Now that's their marking points, so they're not too worried about whether you don't put 1.0 mole per decimeter cubed next to Cu2+. But the salt bridge and voltmeter have to be in there. The platinum electrode has to dip into 1 mole per decimeter cubed of H+, and the hydrogen gas has to be 208K and 1 atmosphere, or 100 kilopascals will be acceptable. This is the final bit, which steps it up again in terms of the level of challenge. It's about constructing a balanced redox equation using oxidation numbers. And the actual example they've chosen is a bit tricky as well. So the first thing to do is to think about the oxidation number of tin. It goes from +2 to +4. That's an increase in oxidation number. So the other species it's reacting with, the iodate, it's iodate 5 in this particular case, must be the oxidizing agent. So for constructing an equation, what I've done is I've just highlighted in blue the things that I might have added in there and the reasons why they have to be in there as well. So in acidic conditions, you must have H+. Any iodine containing anion is likely to end up as elemental iodine unless it's told otherwise, but they tell you in this particular question that the IO3 ions get changed to iodine, so that's not a problem. Now the water it gives somewhere for the H pluses to go, and also the oxygen atoms in the IO3 minus. So now what we have to do is actually look at the change in oxidation number. So like we said, tin goes from +2 to +4. That means 2 electrons are lost by tin 2+ during oxidation. Now you'll see I've suddenly doubled the number of IO3 minuses. Why is that? That's because I've got 2 iodine atoms in my I2 molecule. So if we put in the oxidation number, you can see it's +5 for iodine in IO3 minus and 0 for iodine in I2. That suggests 5 electrons being gained. But it's happening to 2 iodines, isn't it? 2 iodine atoms. So actually there are 10 electrons being gained. So definitely we have an imbalance in the number of electrons being gained here. So let's just collect what we've worked out. The reduction of 2 IO3 minuses requires 10 electrons in total. Oxidation of SN2+ requires 2 electrons in total. So the tin oxidation has to be multiplied by 5, doesn't it? So let's do that. So now we've got something approaching an equation. Let's check our oxygens. There's 6 oxygens on the left-hand side within 2 IO3 minus. So the H2O needs to be multiplied up on the right-hand side to reflect that. That also requires 12 H pluses because 6 H2O means 12 hydrogen atoms. So that's our equation at the bottom. Let's check our mark scheme. And you can see that matches what we're trying to achieve here. Okay, quite a tricky question, quite a lot going on. Hopefully it's been a useful sort of quick tour of the different things you need to be aware of when you're doing redox and electrochemistry. So, as always, thanks for listening. Until next time, see you soon.